Good evening, ladies and gentlemen. The management is proud to present FX and FOBs from Resecurity Labs, ready to school all y'alls on port scanning. Give them a big round of applause right now, FX and FOBs from Security Labs.
Thank you. Okay, I feel like having a déjà vu. I've just been here. Anyway, port scanning improved. You're not going to listen another hour to me. I'm just having the intro slides. First question, why should we reinvent the wheel? Why should we write another port scanner? Yawn. The world changes constantly. Essentially, the world also is full of crappy software. And the requirements for software also change. And when the requirements change sufficiently, it's time to write new software. Because the software no longer fits the purpose it had to begin with. Some software actually never fit the purpose it had, but that's a different story. Now, reality is your measure. What I'm trying to advocate here is redo software. There are times when you need to drop whatever you used so far and write it new. It is only something for people that have a realistic chance finishing the project, because the crappy original is still better than the unfinished sequel. You should actually go ahead and extrapolate. If I start solving this problem correctly in contrast to what I'm using so far, and it's going to take me infinite time, is the problem in infinite time going to get worse or better without my solution? If it's going to get better, wait. You can use your time for other things. Go party, go drink, whatever. Wait, someone else is going to solve your problem. If it's a performance problem on a computer, for example, wait. Intel is going to take care of that. Second rule, don't make a schedule. Because the first piece of software grew over years and years. Yours is not going to be perfect right away, but make it as good as you can. And then set your requirements. Remember, those are your requirements. We had this issue with the port scanner all the time. Don't try to please everyone you talk to. Everyone came like, okay, so you're writing a port scanner. Is it going to do fingerprint, foobar, nmap, blah, blah? I'm like, no, we're writing a port scanner. We're looking for open ports. Don't import requirements from the existing software. Just because you're replacing something, it doesn't mean you have to implement all the features it had, because the features might not have been that useful to begin with. And if you need that feature in the future, you can implement it later. Don't read too much code of the other solution, because at the end of the day, your thought process is going to be as crude as the code you're trying to replace, and nah. We know how that looks like, BSD, Apple, the whole story. Now, there are people who say, well, why should I do that? That's uncool. If you want to research quantum cyber cryptofeminism and its impact on onion-routed RFID 6.2.0, go ahead. We're not saying everyone should do that, but there are times when you actually have to step back from the real cool things and do some work. Because that's what port scanning is for us, work. For most people, port scanning is fun. They find open ports, they get root shells on systems they're not supposed to have root shells on. They need random scanning. They need like lead output. They need 23 different scanning mechanisms to get around IDS systems. But for us, port scanning is work. We need accuracy and we need speed. Because speed translates to the time you're sitting at the customer's place, which translates to money. And we will use dedicated machines. We will not porn surf at the same time with the machine. We're not going to chat at the same time with the machine. We're not going to play Doom at the same time with the same machine. We're using dedicated machines for that. Just to be totally clear, hats off to Fyodor, definitely, because if you have lived in the times before Nmap and you've used like SynScan or ConnectScan or other crappy tools, you loved Nmap. And I really don't miss the times before that. And it introduced many important inventions that may not belong to a port scanner, but hey, things grow. And redo software in general doesn't mean that the original is bad. It just means you need something else. Now, why could we not work with Nmap? The initial trigger for saying, okay, let's write our own port scanner, was port scanning larger networks. And I have to confess, I'm coming of age. There's only so many times per day I can jerk off. And it's not appreciated at the customer side anyway. So waiting for my port scanner to finish to actually start penetrating systems sucks. And the scanner is not lead if it takes 13 minutes and 37 seconds per host. So in a professional environment, you don't port scan systems that are not there. They're powered off, disassembled, carried around the office, thrown away. And when you map large-scale networks, you don't care about this one machine that has the one weird port open somewhere up there in the port range. You care about the big picture in linear time. So on a more abstract level, all the cool features that Nmap has, all the fingerprinting, all the foobar, depends on one single piece of data, which is a list of open and filtered ports. Ever noticed if Nmap doesn't find an open port, all the fingerprinting and everything else goes boom? That's the reason. So we essentially concentrated on getting this list. So our requirements were TCP SYN scanning only, no Christmas trees, nothing else, no UDP scanning, because in a modern world, UDP scanning has zero value. The port is either firewalled or open. In both cases, you don't get an answer, because UDP is a negative scan. It will only produce an answer, named ICMP port unreachable, if the port is closed. Now those cases are gone. We need constant access to result data. We don't want to wait for Nmap to finish and then see what we got. And we use it in dedicated boxes that essentially the idea was get a black box, put the scanner in there, feed it what networks to scan, ship it to the customer, tell the customer, you see, there's a box, plug it in, when it stops blinking, send it back. Bottom line, we wanted a port scanner that does exactly one thing and does it right, which introduces Port Bunny and FOBs, the author of Port Bunny.
Hello. Now that you've heard all about the requirements, let's just see what we made of that and what is so different about our new port scanner, Port Bunny. And to start off with, Port Bunny does something really funny. It actually sends more data than it would have to perform a complete TCP SYN scan and still gains speed on the long run. Secondly, Port Bunny builds a bridge between TCP congestion control and port scanning. And I'm quite aware of the fact that TCP congestion control is not the kind of term you hear every day. And it's certainly not as catchy as Web 2.0. So don't worry about this. We're going to go into this. And most of all, what Port Bunny showed me was that even a simple problem such as a vanilla TCP SYN scan can be extremely complicated if you really want to get it right. Okay, so before we go into all these details, let's just go over the basics real quickly. So if you're going to want to port scan, of course, you want to know which ports you can actually connect to. So what you do is basically you connect to each port in a row, but not completely. You just send a connection request in the form of a TCP SYN packet, and depending on the answer you get, you can figure out if the port is closed, open, or filtered. So if it's closed, you will get a reset. If it's open, you get an acknowledgement, and if it's filtered, and that is something that is often overlooked, you won't get any response. So those are the basics. And that looks pretty easy, so you'd be thinking, what's the problem? Why can't we just, wrap a send call into a for loop and, just wait for the responses and, yeah, then just output the results. Well, that won't quite do it because if you just send as fast as you possibly can, what will happen is the network will just start dropping your packets randomly, and you may even cause a congestion collapse, which means that you're going to be waiting 2 seconds until anything else happens again, something like that. And that, of course, means, if packets are randomly dropped, then you're going to report many ports as filtered, which are actually not filtered, but, the packets were just dropped. And there's another important thing here. There is some kind of optimal speed that you want to find, but this optimal speed, it will change over time, because you are not the only person who's using this network. Other people may be using it, and so you will have less capacity depending on if somebody's starting a big download or something like that. So naturally, the question arises: can the network actually tell us to slow down? And the general answer is no, it can't. There are some exceptions, but they are seen very rarely. There are ICMP source quenches, and then there's ECN for IP version 6, but that's really academic. You don't see that in your everyday network. So the answer is no. The network will just not tell you how fast you can scan. So what info do we have? Well, if you do receive a response for one of your probes, then you'll have a round trip time. That's clear. What about packet drops? Well, if you're absolutely sure that the packet you sent should actually generate a response, then of course if it doesn't, then you can detect a packet drop, but only then. And if you remember, if you're performing a normal TCP SYN scan, you can't know if the port may just be filtered. So if you don't get a response for that TCP SYN probe, then you don't really know if the packet dropped or if the port was just filtered. So that's all the info we have, just round trip times and possibly packet drop detection. Okay, so let's step back a little bit and see how a network model would look like. What environment are we actually playing in? Well, we all know it's a network, so we're not directly connected to the machine. There are a couple of nodes between us, and all these nodes have a queuing capacity, which means that they can save the data and don't have to send it on straight away. And the nodes are connected through different links of different quality. There's the throughput characteristics, delay, and reliability, basically. So one tends to think of this simplified in this way. This probably comes from socket programming. You tend to think of it as a point-to-point connection between two computers. And the term bottleneck basically suggests that there's one thinnest connection that all data has to pass. But that's basically the simplified model you would have. So to regulate speed, to find the optimal speed would mean to find the optimal delay between two packet sends. So that might look something like that. So much for theory, but in practice, finding this optimal delay will fail. And that's the first thing we had to learn the hard way. Because, number one, there's a so-called round-trip time problem, which means that you only know if a packet dropped after a complete round-trip time, which means that once you detect the packet drop, you've already sent all those blue little packets there, and they will hit the bottleneck and cause a congestion collapse. And that's a big problem. And then there's a second problem, and this is far more important. This model here totally ignores the queuing capacity of the nodes. which basically means that, well, we all know you can fire 10 packets at a delay of 0 seconds, and they will actually return. But that doesn't mean that you can take 100 packets, and that will work as well. So the network has this limited queuing ability, and we will have to take care of that. And all of this suggests a new model, which is the bucket model, I called it.
If anyone knows who made the Cisco logo that was placed on the camp door, I'm going to buy him lots of beers.
Okay, so now we have a different objective. We don't want to find the optimal delay. We actually want to fill all the buckets. We want to make use of the complete queuing capacity. But we also have to make sure that we don't put too many packets in the buckets, because otherwise they will just drop. Okay, so yeah, that's basically that, the new question. And now if you look into, let's come back to the TCP congestion control. The funny thing is, these algorithms, which are used in TCP congestion control, actually pose this exact question. It's how many packets can be out there in the network at once, and not the question, what is the optimal delay between packet sends. And if you look into the Nmap code, you will see that Nmap actually makes use of TCP congestion control scheme. Well, it doesn't really implement it, but it makes use of those ideas. And that's the very classic TCP Reno, which dates back to, I think, the 80s, the early 80s. Okay. So the question is, of course, why don't we have this congestion control by default? I mean, if you're downloading something off a website, then of course you don't cause congestion collapses. So somehow that works. But that's just because you're doing that using TCP, and TCP does all of this under the hood for you. Now we are of course sending TCP packets, but in fact we're not dealing with an established TCP connection. They're basically just IP packets, and they happen to be TCP packets. The congestion control only starts after the connection has been established. So you'd be thinking, okay, well, we don't have this out of the box. Let's just take the algorithm and implement it. But that doesn't work, because the situation that TCP is in is quite different from the situation that port scanner is in. First of all, in TCP, the receiver actually acknowledges the packages. And if you think back to the filtered ports, this is not the case when you're port scanning. You may get an answer, the port is closed, the port is open, but also you may just not get an answer. And because of this, in GCP, timeouts are actually error conditions, while in port scanning, a timeout doesn't really mean anything. It just means that you didn't get a response quickly enough. And then something else, TCP has sequence numbers, and we don't really have sequence numbers, and we'll see why that is important. So in other words, the TCP receiver is cooperative, and the host, which is port scanned, is usually not very cooperative. Of course, that doesn't mean that we cannot force it to be cooperative, and that's basically the idea that we're using here. Triggers. Okay. So the idea is this. Before you start the actual port scan, try to find some packets which will generate responses. So for example, you send an ICMP echo request, you send TCP SYN on port 22, and you just see if you can get responses. Now if you do get a response, then this means that, oh wait a minute, no, wait, yeah, if you do get a response, no wait, okay, and then you take these packets that will produce a response for sure, and then you insert them into your probe stream. So you send SYN to port 10, another one to 140, and then you insert your trigger packet, which is the one which will trigger a response, and you go on like that. So what's that good for? Well, the triggers now play the same role, the trigger responses now play the same role as the acknowledgements do in TCP. Because you can be absolutely sure that you should get a response, and if you don't get a response, well, that means that obviously the packet has been dropped. And that means that we get constant information about the network's actual performance. We know if packets were dropped, and we know it straight away. And now a timeout is actually a signal of error, similar to how it is in TCP. So let's take a look at what this means in practice. This is a plot of what an Nmap scan looks like if you're scanning a responsive host. And what you see on the y-axis is the number of packets which are out at once in the network. And you have the time on the x-axis. And of course, the host, by definition, nicely responds to us, so the timing works perfectly. You can see that in a few steps, Nmap kind of converges against the actual limit, the actual capacity of the network in use. Now, what Nmap forgot is what happens when you scan filtered hosts. That's the same plot. But we should be fair about this. I mean, what you see here, obviously, is that since there are no responses, it can't do any timing. So if you're scanning a filtered host, then basically it will just scan as slow as possible. But we should be fair about this. If an answer, let's just read the comment first. This is very nice in the Nmap source code. When a successful ping response comes back, it counts as this many normal responses because the fact that pings are necessary means that we aren't getting much input. So it basically means what they do is this describes a variable which tells us how much a response to a ping would count. And what they do is every 5 seconds in which they have not received an answer, so that's like an eternity, they send one ping probe. And if that returns, it counts as if 3 packets have returned correctly. Okay, so let's give you this in numbers. This is the difference between scanning a filtered host with Nmap on one side, all ports, 12 minutes and 18 seconds, and Port Bunny on the other side, 15 seconds. Okay, so I mentioned sequence numbers. What does this have to do with port scanning? Well, it turns out that sequence numbers can actually be used to detect packet drops early. Sequence numbers, basically you give each packet that you send a number, and this number will also be in the response. So what you can do is, if you've received a trigger response for 5, and then you receive a trigger response for 7, 8, and 9, then obviously trigger response 6 got lost. So you've detected a packet drop before the timeout clock was actually hit. And that's, in many cases, that really helps improve the responsiveness of your scanner. And if you take a look at how Nmap solves this problem without triggers, then you'll see that in this comment, a previous probe must have been lost, which means that Nmap can't detect a timeout, can't detect a dropped packet before it has successfully resent that exact same packet and then received a response. Because then it knows the packet it sent before must have dropped. So that's not really responsive. And an important consequence of this is that Nmap has to resend the packets that could have dropped straight away. And this makes Nmap extremely vulnerable to a problem which we call the late responses problem, which you'll see right now. Because once the timeout clock has been hit, you have to decide to resend. Now you know the clock will not be very accurate, and there may just be some delays for some reason or another. And you start resending because basically you have to know, did this drop or was this just a filtered port? And so you resend, and a little later you get a response for the initial probe. So you've just generated some extra traffic which you wouldn't have needed at all, and it's basically taking away some capacity that you could have used for probes that you actually want to send. And with triggers, you can actually defeat this problem, because you don't have to resend the exact same packet straight away. You can just send any other packet. Because we're not doing the timing depending on the probes, we're doing the timing depending on the triggers. So now overall, what we've done is we've taken the problem of port scanning and we've basically ported it to the TCP congestion control domain, because everything we expect of TCP is now also true for port scanning if you use triggers. So let's go through this. The receiver acts packets in TCP, and it also acknowledges triggers in port scanning. Timeouts are error conditions, and now with triggers, timeouts are also error conditions for port scanning. Sequence numbers are used. Yes, we're using sequence numbers too. We're integrating them into the triggers and are able to detect packet drops early now. So what are the benefits? Obviously, we can now scan filtered hosts, which we were not able to do before, really, because 13 minutes is just too much. Secondly, we can detect packet drops early, as just mentioned. And we don't have to immediately resend the probe which has just dropped or may have just dropped. Most of all, we've ported TCP into the congestion control domain, which means that we can implement other TCP congestion control algorithms, not just the one from 1980, but also new ones. And if you take a look at that development, you'll see that there are many different algorithms for different environments. You'll see algorithms for satellite systems and for wireless networks and all sorts of different environments. And we can make use of all of these algorithms. And that's something really new. Of course, there are also problems with triggers. Not all triggers have the same quality, because let's take an example. Let's use the ping trigger. Let's send ICMP echo requests. Then it may be so that there are ICMP rate limitations, while the probes are not rate limited at all. Then you'll scan a lot slower than you'd have to. TCP triggers are basically the best triggers because they, in most cases, behave just like the probes. This may be different if there's a quality of service, which basically means that you've defined that traffic on some particular port is going to be prioritized. Then, of course, probes may be too slow, or triggers are too slow. So the triggers are not really like the probes, and then that can be a problem. But it's usually not the case. And of course, a host may just not respond to any of our triggers, in which case we think it's down. Okay, how can you fix this? Well, you can at least do the following. You can try to use the best triggers always, which means first try the TCP SYN triggers because they're closest to the probes, then try the ICMP triggers, and last try the UDP triggers because destination unreachables are almost always in somehow limited. And if you find any trigger while you're scanning, if you find a closed port, for example, use it and discard the fallback triggers. Okay, so now we come to the fun part after lots of theory, which is the race between port bunny and nmap. First, we're going to race on responsive hosts, because that should be a field where nmap should be a lot better, because we're actually sending 10% more data because of the triggers. So the question is, can we still win or can't we win? Let's just see. Okay, of course, nothing's for free. But to be honest, when I fixed the slides today, I was searching for, desperately searching for a host where nmap would actually outperform us. And this is what I found. What I did was I plugged a cable directly to my OpenWrt, and in that situation, and I made sure that all the boxes in the apartment were not running, and in that situation you can't do much wrong. And then in fact, nmap beat us. They had 30 seconds, and we had 32 seconds scanning all ports. But that doesn't count much, because, you know, one little bug, or you know, just maybe somebody else is using the network, something like that, and you already have the big differences. 41 seconds for nmap here, 28 seconds for us. Basically, well, this is not exactly the same setup. This is where we're scanning over the internet, so this is where it gets a little more complicated than if you just plug a cable between your home router and your box. And Port Bunny just really often just wins this race, which is kind of pathetic because, like I said, it sends 10% more data. So here's 30 seconds for nmap and 25 seconds for Port Bunny. And then there are serious bugs in nmap. And I think that's, that problem arises when you try to, you know, have 23 different scanning types and you all plug them into one, you try to plug them into one timing code. Then you get things like this. If packet drops are particularly bad, enforce a delay between packet sends, useful for cases such as UDP scan, where responses are frequently rate limited by destination machines or firewalls. And that basically translates to, if packet drops are particularly bad, break the complete timing concept. Because if you're enforcing delays between your sends, then what you're regulating is not really the number of packets out there in the network anymore. You can see this here. We were scanning the iPhone, which was really fun. You'll be thinking, oh, nmap, the iPhone is obviously a performer. Lots of traffic there in the nmap graph. But if you look very closely, then you'll see, I'll show you, this small little gap there right after the start, okay? Can you show it? Yeah. Yeah, that gap, right. That is where packet drops were particularly bad. And now a scan delay was enforced, which means that now the scan delay is actually bigger than the round trip time, which then means that we're sending less than one packet per round trip time, but we're increasing what we think is the number of packets out at once to really high levels, but really we're just sending less than one packet at once. And on the other hand, there's the Port Bunny graph, where you see that there's obviously a limit that's easily detected at about 20 packets or so, and we keep on hitting that, and then, you know, just scanning at a pretty constant speed. And the difference is 24 minutes for nmap and 8 minutes for Port Bunny. Okay, almost done. How much time is left? Enough? Okay. Scanning in parallel. if you Google for port scanners, you'll find a couple of you'll find a port scanner which says, I scan in parallel, and if the port scan goes too slow, then you'll have to scan more jobs in parallel. That's nonsense, and I want to tell you why. The question is, when will parallel scans win, and will they always win? And the assumption is usually, yeah, if we scan in parallel, we're going to be faster. But that's not always true. You have to identify the bottleneck you're dealing with. There are so-called shared bottlenecks among all scan jobs, which basically means, well, yeah, for example, you have a DSL connection, and you just can't go faster than the DSL connection, so yeah, that's shared among all scan jobs. Then the bottleneck can be shared among some scan jobs, and then there's a so-called target bottleneck, which means, which is usually a printer or an iPhone or something like that, just a device which can't handle the traffic that you're giving it. So obviously, if you have a shared bottleneck, there's no real gain in scanning in parallel. That's because a single scan job can make full use of the capacity that's there. And in fact, if you have more scan jobs, then they will fight for the connection, and they will generate losses, and you'll actually go slower than you would have if you had just scanned sequentially. This, of course, assumes that your congestion control algorithm is actually implemented correctly and also works for filtered hosts. Because if it doesn't, of course, then the scan jobs which are scanning filtered hosts are basically they're performing at a very low level, so then it makes sense to scan something else while you're doing that. Now, if you have a target bottleneck, then scanning in parallel makes sense. But that's a lot less frequently the case than just having the DSL connection be the bottleneck. So what does Nmap do? Obviously, it doesn't implement the congestion control scheme for filtered hosts correctly. So what it does is it basically performs the same scheme that it has applied to each of the hosts to the shared bottleneck by counting all responses and all drops. And then you may only send, wait a minute, we'll slow down, yeah. It will only send if both the global system allow it and the timing for the specific host. But that has a lot of problems. One problem is that a badly performing host will keep good performing hosts from firing, which means that this is extremely biased towards the worst performing scan job. And then again, you're not timing the number of packets out at once anymore, because you're keeping scan jobs from maintaining this number of packets out at once. So again, you've broken the concept of the algorithm. So that's not good. So Port Bunny's solution is, since we can actually do these congestion control schemes for all possible hosts, and they have been designed for lots of jobs to be run in parallel, what we do is, in most cases, because of the shared bottleneck, we will scan one host at a time. But you have the option of just saying, I want more hosts now, and then it will just use these. It will just use the timing for each host independently. So there's a lot more research which can be done in parallel scanning. For example, the algorithm which we're currently using, TCP Reno, the one that goes back to the 80s, needs to generate losses to actually find the capacity of the network. And of course, that's not very efficient. And then there are new algorithms such as TCP Vegas, which measure the change in round trip time. That, for example, could be implemented, and the question would be, does this perform nicely, especially if other, network traffic is using TCP Reno, because that's a lot more aggressive. And this is one reason why port bunny is in the kernel. We need extremely precise timing for these kinds of things, for measuring changes in round trip time. Right now, we're not really doing that, but we're aiming at doing that. And also, we wanted to address the scanner bottleneck issue. But to be honest, the kernel is a good place for a port scanner. But for what we're doing right now, I don't think we would have had to do this. But like I just said, it's not a bad place for the port scanner at all. For example, you get a sniffer for free, and this is a quite funny story, so I wanted to tell you. What you can do in the Linux kernel is you can register a callback function, and you can basically register this at the beginning of the chain, which all Ethernet frames must pass. And so that's what we did. So all Ethernet frames first go through the port bunny receive function, and we can choose to drop them or just do things with them and then pass them on and whatever we want to do. So you just get the sniffer for free, and it's really nice. And last, but I wanted to tell you about the user's perspective, because we made port bunny we made it look like a device. We have a device file, and you can basically echo and cat your messages into there, and the protocol is quite simple. Looks something like this: create scan job, whatever, and then set ports to scan and execute it. And then the output would look something like this. So you get the port results straight away. But don't worry, we also wrote a UI, so you don't have to use this echo and cut into the device all the time. It's very simple. You just give it the host, and it starts scanning it. You have a bit of interaction. You can abort the scan job if something goes wrong. You can increase the number of jobs which is scanned at the moment. And about the command line, what's very nice is the /g flag, which generates you data for GNU plot. So the plots that I showed you were all made like this. Thank you. I forgot to tell you about the release. We're going to release this in January, but you can already get a tarball from me directly if you want one. The problem is just that we're still dealing with the licenses and all, so yeah. But it's going to be free for people who can't release. It's going to be free, yeah.